crystallins that give the lens a kind of a reflective surface. And the major function of the lens is to change shape to bend or refract any incoming light, to house that light retina. So refraction is something that you could sort of put as maybe a one-word answer there, where it says, what is the function of the lens? Or focus, another one, focus the light. It's not the only thing that focuses. In fact, if you look at these images down here at the bottom, the cornea also does a lot of focusing of the light as well. And so the cornea and the lens together help to focus. And when the lens refracts the light, it can actually change its shape based on whether an object is close to your eye or far away. And that's referred to as accommodation. The term accommodation basically is the term for when the lens changes its shape to keep an image focused on your retina. And when you're looking at objects that are far away, the lens flattens. It kind of flattens out. The ciliary muscles relax, which kind of pulls the lens flat. Those ciliary muscles are round, like a hoop, like a hula hoop around the lens. Or, like I said before, like the lens is like the center of a bicycle wheel, and these are spokes. So the ciliary muscles are kind of like the bicycle tire all the way around it. And when those muscles relax, they actually kind of pull outward, which stretches the lens flatter. And that's how you see objects that are far away. As an object moves closer to you for closer vision, those ciliary muscles contract tighter and tighter, which allows the lens to bulge and get a little thicker in the middle, which focuses the image on the retina for things that are closer. Very near vision, that's part of the reason it's contracting. That's the reason why reading and studying for long periods of time can actually be very tiring. When you think about your eyes getting tired, there's lots of energy required. But reading anything, and by the way, near object is kind of defined as anything closer than 20 feet, right? So if you're studying and reading for hours and hours on anything that's closer than 20 feet, you are working your ciliary muscles to maintain focus on that object. That includes your anything like that, and very, very exhausting for your eyes for anything closer than 20 feet. Okay, so the lens will flatten for objects far away. It will bulge or get more rounded for objects that are very close. But that bulging requires ciliary muscle contraction. Okay, and all of that together, this movement together, is referred to as accommodation. My ciliary muscles are tired. Yeah. I mean, and you know it. The thing is, I notice that I don't notice it until I'm just exhausted. My whole body's just kind of tired from studying, and I can't do it anymore. And I just kind of sit down and veg out in front of the TV or something like that. Because in my house, the TV is, far enough away that it doesn't require too much accommodation. I don't really take that into consideration, but it definitely is more relaxing than trying to read and study. And I notice it's exhausting. Those of us who wear glasses will also notice sometimes that those extra muscles can hurt to feel, those eye muscles get sore, and they can get sometimes, just like regular muscles elsewhere in your body. So if this is the reason why I wanted to cover that part about the lens over there on 190, and then we kind of skip over to 191. talking about refraction, how light bends as it comes into the eye. And when you're looking at an object far away, the light is refracted um, from far away. The light is more parallel and then get bent onto the retina of the eye, but that's easier to do than for objects that are very close. So it's easier on the eye to look at objects that are 20 feet away or further. And that's, again, you can just kind of read about that. It's nothing that's in bold, and if it's a little confusing, don't worry too much about it. But when you look at an object close up, the light rays enter the eye and have to be bent. So that's kind of this image right here. When you're looking at a closer object, like this little red dot down here in the lower left, right there, the light rays from that closer object are not as parallel as they are from a far away object. So they have to be bent even harder and further, so that requires that extra bulging in the lens. And as long as, let's skip kind of to the main point, as long as that is all working well, the focusing and the accommodation is working well, then whatever it is your eye is pointed at will be focused on your retina. That image will be focused on your retina, and your retina will be able to make a sharp image and send that to the thalamus and then the occipital lobe, right? That's referred to as emmetropia, normal vision. Emmetropia. Now, if your eye kind of over focuses the beams of light, if it over focuses, or the eyeball is a little bit oblong, then the lens will focus the image, but it's focused in this empty space. Well, its focus is in the vitreous humor. Those light beams will scatter a little bit before they actually get to the retina. See if I can kind of simulate it a little bit. They'll kind of scatter a little bit further, and you don't get a sharp focused image at a point. You get a blurry point. You know, that red dot would look blurry like it does when I just look at it on my screen. It looks blurry without my glasses on. So it's kind of blurry all the way around. If that's the case, that's referred to as myopia, what we sometimes call nearsightedness. We sometimes say it happens because the eye is too long, phrasing it, or we could also say that the lens over focuses or over accommodates. It does too good of a job, and it sharpens the focus before the image actually gets to the retina. So we can adapt that with a lens, kind of a concave, diverging lens that kind of spreads the light beams out a little bit more before they get to that super awesome over-focusing lens. And we adjust the lens, or the ophthalmologist adjusts the lens until we are able to look at the object and it looks focused to us. It looks sharp. The opposite of myopia is hyperopia. We sometimes call that farsightedness. This is where the lens maybe doesn't focus enough, or the eyeball is a little bit too short. It's a little bit shorter. If the eyeball was just a little bit longer, then the lens would give us a sharp focused image right there on the retina, but it doesn't. It hits the retina and it's still blurry. It's not fully focused. So that's what we call farsightedness. And we kind of use an AVA lens that helps the lens do what it's not able to do as much without the lens. The light beams a little closer together before they enter the lens. So these are ways of helping the lens. And then there are kind of other issues that happen. Astigmatism is a problem or an irregularity in the cornea. It says in the cornea, but it could be in the lens also, to be honest. The astigmatism could be an irregularity in the cornea, a little bump in the surface of the cornea, but it could also be within the lens. And it is blurriness at all distances. So let me kind of back up a little bit. The thing about nearsightedness, myopia, sightedness, it actually does a pretty good job at focusing on things up close. So people with nearsightedness or myopia, things might be pretty sharp and pretty clear if they're less than 20 feet away. But if they get more than 20 feet away, they're more blurry. So that's why we refer to myopia as nearsighted, because their sight is good up close, because they have this lens that's doing a great job of, like an great job of over focusing, and that works really well for close-up objects. Farsightedness, it's fine. The further away an object is, the better, because the lens is not doing a very good job focusing. But if it's far away, those beams are more parallel and don't need a lot of focusing. So the further away the object is, the less work the lens needs to be able to do. So things that are far away are usually clear, but the closer they get, the blurrier they get. There's a version of this farsightedness that happens with age. It comes from the Greek word presbyos, which means elder. If you've ever heard of a branch of Christianity referred to as Presbyterianism, it comes from the same Greek word. Presbyterian means elder-led, or led by a group of elders. So if you've ever heard presbyos, you've probably heard it in the terms of Presbyterian, but it's also just a word that means elder, and presbyopia means elder vision. This is at the top of page 192. Elder vision. It is a form of farsightedness. The distant vision might be fine, but the closer the object is, the blurrier it tends to get. So that's just because the lens gets a little more stiff or rigid the older we get. One of the many things to look forward to for having a long, happy. I want to live a long, happy life. Yeah, well, the more stuff you have to quote, look forward to. Pardon the pun. I keep mentioning the 20 feet business. The 20 feet. That's kind of an important number when it comes to measuring visual acuity. So if we say that somebody can see an object clearly from 20 feet, but it gets blurrier as the object is closer, then there's that boundary between near vision and far vision. And the guy that discovered this, you don't need to know his name, but his name was Snellen. And I think he was a Dutch ophthalmologist. And he was the guy that actually discovered that 20 feet is kind of the standard distance between what's called near vision and far vision. And he developed a chart called the Snellen eye chart that everybody has seen. Something like that, You've seen these charts before and might not have known that they're referred to as the Snellen eye chart. He developed that, and you look at that chart with one eye at a time from 20 feet away. That's kind of the standard distance. And you read the first line, then you read the next line, and then read the next line. They don't do this as much anymore at the optometrist. They have different ways of doing it. But it still is based on this standard 20 feet away, and that's where the numbers 20/20 vision come from. But they don't refer to each eye. The two numbers refer to your eye, you, compared to the standard. Standard is is what that's supposed to say. So it says you can read. So each eye has two numbers. Each eye has two numbers. So your left eye, if we say your left eye is 20/20, what we're saying is your left eye can read a line of text from 20 feet, what the standard eye can read from 20 feet. Okay? What if you have 20/60 in your left eye? Again, both numbers for one eye. That says that your left eye, this is your eye on the left, the first number is you. Your left eye can read a line of text from 20 feet away that the standard eye can stand 60 feet away and read it. You see how that's worse? The standard vision could stand 3 times further away and read that line of text. You have to move all the way up to 20 feet for it to be clear and be able to read it. So 20/60 is worse than 20/20. 20 is just kind of standard. Then these tests are called tests of visual acuity or sharpness, testing for sharpness. That's mentioned at the bottom of page 190. So each eye will have a pair of numbers. So 20/40 in my right eye and 20/50 in my left eye. So we have two numbers. And so again, the first number is my eye. So my left eye by itself could read a line of letters that people with normal vision could stand at 50 feet. They could stand much further away. They'd be way back behind me reading the same line that I can barely read at 20 feet. Those numbers make sense a little bit now? That's called visual acuity, just distance visual sharpness. But the 20 is 20 feet, based on those measurements made back at the turn of the 20th century, the early 1900s, by, I can't remember his first name, Snellen. Feel like I should Google it now. The Snellen eye chart, Herman. Somebody Googled it already, didn't you? No, you didn't. Good. His name was Herman Snellen. That should be easy to remember. His name rhymes. Yeah, but that's what we're measuring when we're measuring visual acuity, and that's the reason why both eyes will have two numbers. Now about the visual pathway. Now the stuff at the bottom of 192, photoreceptors, we kind of talked about already. But the visual pathway, the main thing to know is just sort of the sequence of events that things have to pass through on the way from the retinas to the occipital lobes. But most of this we've already traced, we've already followed it. So we've already said that light coming into the eye passes through the cornea, aqueous humor, pupil, lens, and then it's going to hit the retina, and it will pass through those ganglion cells first, then bipolar cells, then photoreceptors, and then it will generate action potentials. These are known as the visual pathways. It's actually a sequence of action potentials. So at the very top of 193, that's kind of what's at the way upper left. We're kind of picking up the action potentials from there. The photoreceptors will send action potentials to the bipolar cells, then to the ganglion cells. The ganglion cells technically are the optic nerve, but the optic nerve of each eye goes back to the middle under the brain, right about where just over sella turcica in the skull. And some of the fibers of the optic nerve will cross over to the other side, forming what's known as the optic tract. The optic tract. So we have optic nerve, the crossing place, which is called the optic chiasma, or in the textbook they don't put the A at the end of it. Either one is fine, optic chiasm or optic chiasma, that cross, some of the fibers cross, and then what comes out behind it is not a nerve anymore. It's called the optic tract, to the thalamus, then to the occipital lobe. So we kind of talked about that already. But the significance, the crossing fibers, don't worry about drawing the image of the optic chiasma, but the significance of the crossing fibers is, if you kind of follow this stuff that's sort of in red over here, this is the stuff, if you were looking at it, is way out here to the right side of your field of view, way out here to your right. And it's going to come in, and the lens is going to make that flip to the left side of each retina as you're looking at the object. So say you're looking at this spot right here, and if you keep your eye looking right at that spot, there's this stuff out here in your periphery. And when you're looking at that spot, there's kind of this middle line where everything from there to the right is going to go to the left side of your retina. You don't have to worry too much about how this works, but I'll tell you kind of how the consequences of it come out. So those fibers coming from that retina of this eye will stay over here and head back to the left occipital lobe. But going back up here to this other eye, the same field of view, out the peripheral vision to your right, those action potentials will cross and join those from the opposite eye and go to the left field or the left occipital lobe. So here's the big takeaway. Here's the big point. Why the crossing of the retinal fibers is significant. Everything to your right field of view will be processed by the left occipital lobe. Everything from both eyes, the stuff from your right eye is going to cross over and join the fibers from your left eye to go to the left occipital lobe. But that means that everything from your right field of view, like if you're looking directly at this middle point, everything out to the right for both eyes is going to be processed by your left occipital lobe, and vice versa. Everything to your left peripheral view from the center left is going to be processed by the right occipital lobe. Now that's all the in-between of how it works, you don't need to worry about. But that's like the big takeaway point. Okay, and what did we call that? What do we call that when one side of the brain controls or processes the other side of the body? What's the term for that? Wow, you typed that fast. I didn't even have a chance to take a sip of my coffee, Cheryl. So even visual processing is contralateral. Even visual processing is contralateral. I think that's the big thing. That's a way to kind of summarize in that small space. Why is the crossing of retinal fibers significant? Things that are processed by the occipital lobe are contralateral. Now, one big thing here too. I said this just a second ago. I'm going to put it right in here. I'm going to make it purple because it's a pituitary, and that pituitary sits right there. And with a pituitary tumor, the kind of vision that's lost when the pituitary tumor pushes on the optic chiasm, when it smashes up against the optic chiasm, the kind of vision that you lose is the pathways that cross. And the pathways that cross are those from the peripheral fields of both eyes. So if a patient comes in and their complaint is, for the past few days, I've noticed that my peripheral vision on both sides is starting to close in. I feel like I'm losing my peripheral, or I see I see sparkles or starry shaped things in the peripheral view of both eyes, that's almost always a sure sign. It's called hemianopsia, bitemporal hemianopsia. And you don't need to memorize that right now. If it's ever relevant for you in your career, you'll get to it. You'll come back and you'll go, oh, that's that thing that Nichols said way back in A&P 1. I remember him saying that. But it is a loss of peripheral vision in both eyes, slow and progressive loss, and it's almost always a sign that there's something wrong with the pituitary. So that's what's significant about that. All right, ready to move on? Are you ready to move on? Let's go back and take a look at those questions that I skipped here. What's the function of the ciliary body? The function of the ciliary body. What's the function of the ciliary body? You guys take a look at that one. Tell me, what's the function of these choices? What would be the function of the ciliary body? The ciliary muscles contract the muscles of the iris. No, they contract the lens. Contract the lens. The ciliary body does have ciliary processes that secrete aqueous humor. Yes. Yep. That's a good one. Process visual stimuli. No, those are the photoreceptors of the retina. Definitely not. Moving the eye. No, that's external muscles called the extrinsic eye muscles. Nope. Lysozyme to kill bacteria. No, that's the lacrimal apparatus. So this first one's a little tricky. The muscles of the iris are controlled independently. They're controlled by the oculomotor nerve, but they aren't controlled by the ciliary body. The ciliary body has two parts. It has ciliary muscles that change the shape of the lens, and it has ciliary processes that stick out that secrete aqueous humor. Collectively, these two parts are the two main parts of what's called the ciliary body. So that was phrased in a kind of a confusing way. Increase in aqueous humor leading to increased intraocular pressure. We talked about that one already. Glaucoma. And so there we go. Let's move on and talk about hearing. It's a little bit shorter. It's not quite as complicated. Sensory receptor of the pupillary reflex occurs during accommodation for distant vision. The lens ciliary muscles relax and the lens flattens. Sensory receptor for the pupillary reflex. This is shining a light in somebody's eyes. So those are, excuse me, photoreceptors. Sorry. Got a little pollen in my larynx here. Good opportunity to sip some coffee. So definitely a little bit more straightforward, not straightforward, but definitely not as complicated as understanding vision is the ear. Like the eye, so we talked about the eye having 3 layers. The ear doesn't exactly have 3 layers, but it's got 3 distinctive zones or sections called the external ear, the middle ear, and the internal ear. You can see the boundaries, the boundary between the external and middle ear, excuse me. The official boundary between the external ear and the middle ear is called the eardrum, officially known as the tympanic membrane. And the boundary between the middle ear and the inner ear is, we can't really see it, but it's this membrane under this oval called the oval window. This is just part of this little bone that we'll talk about here in a minute as well. But the official external ear actually includes the tube that goes into This bone right here. What bone is this? All of this. Is it labeled? Let me see. Yeah. It's on the diagram. I'm not going to point it out. I want to see if you can guess or just find it. What bone is your ear embedded in? Your ear structures. Yeah, the temporal bone. All of this is within your temporal bone. Exactly. And some of this is just tubes, cave-like twisting tubes within the bone itself. But there's a hole in that temporal bone that you studied when you studied the bones of the skull called the external auditory meatus or the external acoustic meatus. And that hole in bone is named for the tube that leads into the ear. So this thing that we sometimes call the ear is actually just the auricle that helps to channel sound. Remember, it's that your ears are one of only two places in the body that contain elastic cartilage. The epiglottis in your throat, in the pharynx, is the only other place that has this unusual and unique type of cartilage that helps maintain the shape of the auricle. Then we got the external auditory canal traveling through the temporal bone. What glands prevent foreign objects from moving deep into the external auditory canal? What do they secrete? They're a modification. They're kind of a modification. What are they specifically? They're only really found here in the external ear. They're a modified sebaceous gland. Anybody remember what they're called? They're called ceruminous glands. What's the word cerumen mean? Come on. This goop comes out of your ear. You know it. Earwax. Yeah. It's a thick oil that's actually waxy. It's a little bit waxier. So it's a highly modified version of a sebaceous gland, which is an oil gland, but it secretes a thicker, waxier lipid that's called cerumen, earwax. Yeah, and that's how it kind of keeps the canal clear and tends to secrete and push material out this way. So that's why your earwax is always dripping out and or falling out or whatever. Some people have really dry earwax that has a little bit of lipid and a lot of cellular material, and others have a lot of lipid that can kind of ooze out. So anyway, enough of that. I've grossed you out enough today. The tympanic membrane is kind of the wall between the external ear and the middle ear, but also you can see in parentheses there, sometimes included with the middle ear, because it's sort of the same as, looking at a wall between two rooms and saying, which room is this wall a part of? Well, both, sort of. So the tympanic membrane is kind of like a wall between the two, and that's why it's fair to kind of say it's technically sort of part of the external and the middle ear. But its structure its job is to vibrate. It's a dense, regular connective tissue that vibrates when sound hits it. And its major job is to vibrate these little bones behind it. The first bone is directly attached to the tympanic membrane. An external ear infection called otitis externa. Typically, we sometimes call it swimmer's ear. You don't necessarily get it from swimming in contaminated water, but that is a common cause of it. And even if you weren't swimming in contaminated water, they might still call it swimmer's ear, but the medical term is externa. And then we get to the middle ear, and the major job there is these little bones. Say I've got a better picture of them. A better image of, here's that tympanic membrane vibrating with sound waves, and it vibrates forward. It vibrates the first of these bones that's attached directly to the tympanic membrane, called the malleus. The malleus vibrates the incus, and then the incus vibrates the stapes. And so all three of these bones together help to transmit the sound waves from the tympanic membrane, which is basically vibrating air. That's what sound technically is. Sound waves are technically air vibrations. And so the job of these bones is to transmit that sound over into the inner ear, which is filled with fluid. So the job is to kind of turn air vibration into fluid vibration in the inner ear, and that fluid vibration is what gets transmitted to the brain as sound. So these middle ear bones play a really important role in transmitting that sound. By the way, I don't think that you need to know this, but I think that Dr. Schultz talks about this a bit in the video. What does the word malleus mean? What's the malleus? What is the word malleus Latin for? And does she talk about it? I can't recall if she talks about what these names mean. I guess she doesn't. You guys are just giving me some radio silence. See if I can draw this in a way. Let's see if I can. The word malleus is a word for hammer, but there's a type of hammer that's directly named from the word malleus. What is a type of like rubber hammer? Anybody know this one? A mallet. Yeah, a mallet. The word mallet is really almost directly from the Latin word for hammer. Then there's, I hesitate to draw this one, but I will do anything to help you guys try to remember this stuff. Oh my gosh. This is like that silly game Pictionary or something. Think blacksmith shop. Think shaping horseshoes. And the blacksmith hammers onto this giant metal thing that he uses to shape the metal, called an anvil. Yeah, that's what the word incus is. And that's why somebody named these two things. The malleus hits the incus. To me, neither one of them looks anything like what it's named after. And then stapes does look exactly like what it's named after. If you picture the side of a horse saddle where you put your feet, what's that called? Those two things on either side of a horse's saddle where you slide your feet in. A stirrup. That's what the word stapes means in Latin. It refers to stirrup. And it's the only one of the bones to me that looks anything like what it's named after. But I love horses, and I do like the whole blacksmith horseshoe stirrup theme that somebody kind of gave to these three bones. Now, of course, we want you to know the official medical names for each one. Malleus, incus, and stapes. Malleus, incus, and stapes. But their basic job is to transmit that sound across the middle ear. A middle ear infection is called otitis media. They're very common in children because there's this tube right here that didn't show up too well. Let me make it a lot lighter. There's this tube right here that's referred to as the eustachian tube or the auditory tube, and it connects to the back of your nasal cavities. And it's really common for bacteria from your nose to get from the back of your nose to kind of get up into this middle ear. It's not that common for adults, but it's extremely common in babies and children because this tube is a lot shorter distance for that bacteria to get up into the middle ear. So middle ear infections, otitis media, are very, very, very common in children. Now, what is the job of this tube? What is the function of this tube? Please hold on. Before you finish typing, it's not drainage. The ear doesn't really make any fluid that needs to be drained. It's not for drainage. If you watch the video, though, she talks about it. I guess there is some stuff that does drain, but that's not its primary major function. What's the function of this tube? Balance of what? You must be more specific. Throwing out random individual words. Equalizing air pressure. Look, to equalize, not balance and equilibrium, not balance and equilibrium. That's the inner ear, way over here pictured on our diagram. But look at this. Remember this tympanic membrane. This is a closed, nope, not movement. The answer is there already. Ernestina gave it to us. Equalize air pressure. Look at this membrane right here. That's a closed membrane. But this side of the membrane, the outside, coming from the outside world, it's open to the air. This side over here is closed off. But when you yawn or swallow, this opening to the back of your throat opens up and equalizes the air pressure in the middle ear, makes it equalize with the outside pressure, with the air pressure. So what happens when you drive high up in the mountain? You take an elevator to the 34th floor of something in downtown Atlanta, you get on an airplane and you start flying up high, and the outside air pressure begins to change. As you go higher, the outside air pressure actually gets lower, and it starts to pull your tympanic membrane towards the lower pressure. As the tympanic membrane gets tighter, it doesn't vibrate as much, so the sound becomes muffled. But if you yawn, pharynx down here in the back of your nasal cavities, by yawning or swallowing, you open up this tube, which is normally partially collapsed, but you open this up and you allow the air pressure to equalize on both sides, and that lets the tympanic membrane pop back into its middle position so it can vibrate normally. Okay, well, all right. So a middle ear infection can impact equilibrium, but that's an all-out, that's a flat-out infection. That's a full-out infection. And it can impact equilibrium because the infection can put pressure on the bones right here and just on the other picture of them. Just on the other side of those bones, here's the middle ear. It's real tiny. There's the middle ear, but just on the back side of these bones are these semicircular canals that control equilibrium, and pressure there from the infection. I'm not talking about air pressure. Pressure from the infection can bend those bones and cause not unregulated stimuli to the brain think moving or not. Does a Q-tip reach to the middle ear? Only if your tympanic membrane is broken. Keep the Q-tip out of your ear, people. Keep that Q-tip out of the acoustic meatus. If I stick it, let's see if I can draw a Q-tip. Just a little tip from your Uncle Rob, guys. That Q-tip was not made to go in the ear canal. There it is. Does it reach the middle ear? Only if you have done serious damage to your tympanic membrane. Yeah, the tympanic membrane is a living organic structure that should be able to repair itself, but does not always repair itself completely properly. Yeah, the auditory tube's major function is air pressure. Equalize air pressure. That's it. 3 words. Equalize air pressure between the middle ear and the outside world and the external ear. Yep. It does allow for a little bit of drainage, but the downside of it is it also allows bacteria from the back of your nose, which is nasopharynx. It can allow bacteria to work its way up through here. So it's really common for people that have regular sinus infections and pharyngitis to get middle ear infections. Like I said, that tube is a lot shorter in children, so middle ear infections are much more common in children than they are in adults. And a lot of kids that have frequent otitis media will grow out of it just because the bones get bigger and that tube, that auditory tube, gets longer as we grow. So if you've got a pediatrician that kind of is saying, don't worry, they'll grow out of it, you know, and you kind of roll your eyes and say, yeah, you say that now. That's because most kids will. Most kids will. But you don't want a kid to have such a, you know, like what Tristica is saying about otitis externa or otitis media. If they're very severe infections that are not able to be treated by antibiotic, they could damage the tympanic membrane or the auditory ossicles, those bones, and it could cause, you know, permanent damage to the hearing. Now let's move on. The inner ear. The inner ear consists of these tubes that are actually embedded within the temporal bone. Some of the tubes are these tubes called semicircular canals that are for equilibrium. But there's this other one long tube that has a lot of different subdivisions in it that looks just like what animal? What does that look like? Come on, y'all. Quick on this one, right? And what is, now you know some Greek, because what is the Greek word for a snail? What's the Greek word for snail? You don't even have to change the word at all. Type it just like it shows on the screen and tell me. Cochlea. Yeah, the word cochlea is the Greek noun for a snail shell, a spiral snail shell. Isn't that beautiful? I love it when stuff gets named exactly for what it looks. Now, what it really is it's not a snail shell or really a tube in your bone. It's actually a spiral-shaped cave or cavity within the bone. And I really love the image that we have on page 194 that kind of shows what the cochlea might look like if we stretched it out, if we rolled it out. Because if we roll it out, you see that there's actually one tube that sort of goes all the way out to the tip of the snail shell and then turns around and kind of comes back. And this is how the sound vibrations go through your cochlea. Let's see if I've got a similar illustration from the textbook here. Yeah, that was pretty good. This is the one, yeah. This looks a little bit different than the one. The one on 194 is actually better. But when the stapes vibrates the oval window, all of this up here is filled with fluid. And it will vibrate the sound out from the oval window. And if the sound frequency is at a certain frequency, it will actually bend the membrane between these two spaces that contains the organ of Corti. I'll show you that in just a second. But there's actually millions of tiny little cells all along here. And if you bend it, if vibrations bend it, it stimulates them to generate action potentials. At a certain frequency, it gets bent, and it goes back and forth. It bends and wobbles back and forth. Kind of like, let me see if I can. It'll kind of bend down and sort of go like that real fast, like hyper fast. You hear a sound and then it's over, and that was just hyper fast. And so as it passes through from oval window, it passes along and generates a vibration in the membrane. Oh, did that sound like a cool Jedi sound? Well, I've been practicing. I have a 4-year-old Padawan at my house who is right now watching the Clone Wars episodes while I'm in class. And he's going to be so disappointed when he finds out the entire Star Wars universe is fictional, because I think he really is ready for Jedi Academy. So there's my Jedi sound. There. And so it kind of vibrates the membrane, but then the rest of the vibration curls out to the end of the cochlea, comes back and kind of hits this round window, and this round window is kind of like a pillow, and it dampens the sound and keeps it from bouncing back so we don't hear an echo when we hear the sound waves. So that all of that is actually curled up in this thing called the cochlea. So here's a little sound wave hitting the oval window from the stapes, and the frequency of the sound will vibrate a certain spot along this membrane called the organ of Corti. It's embedded in this basilar membrane. And the cells along here detect very specific vibrations. So the really high frequency sounds are the ones close to that oval window. And all of the lowest frequency sounds that you can hear are way up here near what's called the apex of the cochlea. Now, I don't see any of that in your notes, so that was extra. Don't worry about memorizing it. But that's kind of what that does. That's how that functions. So that's sort of how sound works. That's the as simple as I can explain it. It's like everything in life. It's more complicated than that, but let's don't overcomplicate it too much and keep it how you need to know it at this level. So there's the cochlea. The cochlea is specifically for hearing sound, okay? This whole thing that's painted in purple here, called the spiral organ, is laid out very much like a piano. So it's very much like the keys of a piano, with all of the really high frequencies on one side and all the real low frequencies at the other end. And that's how it is. Most of the sounds that you hear on a day-by-day basis are somewhere kind of in the middle. But the highest frequency sounds that you can possibly hear, the super, super high-pitched sounds, are right up here. And the super low sounds, the lowest sounds that you can hear, are all the way at the end of that organ, and everything else in between. Now, sticking out up here, let me go back to my original picture so you can sort of see where all of this stuff is. There's the cochlea, and remember, embedded in that are those two channels of fluid with kind of a third one in between, and they process hearing. There's the oval one, vibrates that fluid. It kind of goes all the way out, and the vibrations turn around and they'll come back and hit that round window like a pillow, again, that kind of dampens the sound and prevents the echo. But look way back here. Right back in here are a set of 3 tubes, and those 3 tubes are referred to as the semicircular canals. And those semicircular canals have these enlarged areas at their base, and those big enlarged areas are referred to as the ampulla of the semicircular canals. So those ampulla areas of the semicircular canals, these kind of enlarged areas in this whole area here, is called the vestibule. The reason I want you to be familiar with the word vestibule is the cranial nerve that's in charge of all of this hearing and equilibrium is cranial nerve number 8, which is referred to as the one big word, vestibulocochlear nerve. The vestibulo part of the nerve is equilibrium. The cochlear part is for hearing sound. Okay, for auditory hearing. Okay, there's 2 different kinds of equilibrium. There's the equilibrium of movement of your head. So while you're moving or rotating your head, not getting dizzy is the responsibility of the fluid in these semicircular canals. So at the base of those semicircular canals are those enlarged areas called the ampulla that have these little receptor cells with little cilia hairs. And when those hairs bend, when the fluid moves, that's the ear's way of telling the brain we detect movement. And if the brain agrees and said, yes, I did make the head move, that's no surprise to me, then everything's fine and the brain kind of ignores it. But if the ear tells the brain that the head is moving, but the brain did not initiate any movement and the head isn't really moving at all, the brain gets confused. And that's the dizziness that we call vertigo. And vertigo can be caused by a lot of things. As we already mentioned, a middle ear infection that presses on the bones can actually stimulate movement in the fluid when the head is not actually moving, making the brain confused that is it moving or is it not? And so the stimuli coming from the ear make it feel like the head is moving. And notice the shape of these semicircular canals. That's why vertigo sometimes feels like the head is spinning or rotating, because when these are working normally, it does involve fluid spinning through these canals, but the brain agrees with it. The brain says, yes, I did turn my head to the left, and so that fluid shifts a little in response. It's exactly what was expected, as opposed to the brain getting a signal from those semicircular canals. The semicircular canals say, oh, you turned your head to the left, and the brain goes, no, I didn't. And it gets really confused, and it keeps sending these signals repeatedly because of the pressure from the middle ear, the pressure on those nerves that keep sending false or fake stimuli, and can obviously make a person feel dizzy, lightheaded, like your head is swimming, but going around in circles. When everything is working normally, these ampulla, these receptor cells, send impulses to the brain about fluid movement. Now, down in the larger area called the vestibule, which is more, let me kind of do it in a color that'll stand out a little better. Down in the vestibule, which is more down in here, in this area, are these structures that just monitor head position really when not moving. Okay, so for example, when you lay down your head to go to sleep at night and you lay down your head on the pillow, your brain will still kind of monitor the head position, even though it's not really moving. And even with your eyes closed, you'll be able to kind of mentally picture what position your head is in. Like it's either, you're laying on the back of your head with your face pointed toward the ceiling, or you're laying on the side of your cheek. And even with your eyes closed, you can feel the position that your head is in. When you're standing up, but not moving, you can feel the position that your head is in. This is the way that the brain does something similar to proprioception for the head. And that's called static equilibrium, or non-moving equilibrium. Just understanding the balance of the head while it's not moving. Couple of final notes on hearing that I think are important to know. There's some other stuff that one bold-faced term at the top of page 196. Definitely know the term pitch, which means the frequency of sound. And then it's got, what I already mentioned, the high frequency sounds near the oval window, low frequency sounds at the end of the scala vestibuli, which is at the tip of the cochlea, the middle part of that circle. But deafness is definitely an issue to talk about, for future clinicians. And there's really two major types of deafness: conduction deafness and sensorineural deafness. Conduction deafness involves damage to those structures that actually transmit the vibrations to the cochlea. So that could be any blockage of the external acoustic meatus, blockage, like wax in the ear canal, right? Damage to the ossicles, damage to, which could be caused by otitis media, damage to the tympanic membrane. I didn't put this on my tympanic membrane too. I should have had that on my list. All right, so otitis externa, swimmer's ear can damage the tympanic membrane or the malleus right behind it. Middle ear infections can cause permanent damage to those bones. There are some congenital aging diseases that happen because each of those bones. Do you guys? Let me ask you this question. I know you're about half asleep and we're almost done for the day. What do you call bands of connective tissue that connect bone to bone? What do you call bands of connective tissue that attach bone to bone? Not a cartilage. You might find cartilage, but the connecting bone to bone is a ligament. Those are called ligaments. Exactly. And ossicles of the middle ear. Let's see if we can sort of see them. Yeah, not really. Not really. Maybe this other image had them a little better. Sort of. There is a ligament right here that kind of holds the malleus against the wall of the middle ear, but each of these bones is also attached to each other and held together by ligaments. Well, over time, these wonderful, lovely ligaments can harden. They can get more rigid, meaning you don't get as much, you get just less vibration out of these middle ear bones, these ossicles. So that's a cause of conduction deafness as well. Damage to any of the structures or just failure of function of any of the structures that transmit vibrations from the outside world to the cochlea. Now, once we get in the cochlea is mostly neural. So the nerve sensory pathway, so the damage to the cochlea itself, damage to the cranial nerve number 8, vestibulocochlear nerve. We sometimes call this nerve deafness or nerve damage, but the official medical term for it is sensory neural damage. So conduction deafness could be caused by damage to the incus, malleus, tympanic membrane. Penna, which, by the way, I don't think I mentioned this, but I want to make sure I do. That's the other name for the auricle, or that big thing that sticks out of the side of your head that we call ears. And this is all of the above. Conduction deafness could be caused by any of those. Where are the sensory receptors for balance found? Well, those are specifically in the semicircular canals of the inner ear, of the internal ear. What is I've seen that. I want you guys to do this one. I've seen this as a short answer question on past tests. What is the function of the vestibule? I want you to give the answer in 2 words. Give your answer in 2 words. Go back and look at it. We just looked at it a minute ago. Don't over-explain it. Give me an answer in 2 words. Page 195. 195. It's right next to the word vestibule on page 195. Yeah, there it is. Just wanted to see who could type it fast enough. Static equilibrium. Static equilibrium. Another version of the question would say, what is the function of the semicircular canals? What would the answer be if the question said, what is the function of the semicircular canals? What would be the answer? Dynamic equilibrium. Good, yeah. Don't have to overdo it, over-explain it, whatever. Just kind of leave it at that. Okay? So, how about this next one? The stapes sends sound wave vibrations directly to which structure? I'll buy it. That sounds good. Yep. Sounds like a good explanation to me. Oval window. So the stapes is directly connected to the oval window. It communicates directly to the oval window. Okay. Now how about which of the following would be classified as sensory neural deafness, sensory neural deafness. Yeah, damage to anything else here. Anything else. There's another word I didn't mention. The antrum is the space around the ossicles, the little bones. So the space around the ossicles is called the antrum. So if there's fluid buildup in the antrum, yes. Damage to the tympanic membrane, damage to the malleus, incus, or stapes, any one of these three would be called conduction deafness. Damage to the cochlea, specifically sensory neural deafness. Let's see, one more. Oh, see how nice this is? Got it in a nice multiple choice question where you're kind of like, all you got to do is just not pick the wrong answer. One of the tricks to watch out for is there is a tendency to say, "Oh, that's for fluid drainage." You know, that's all about fluid drainage. Technically, there is a little bit of drainage, but that's not the main function of the eustachian tube. Its main job is to equalize that air pressure between the middle ear and the outside air. All right. So I literally have exactly 2 slides left to do smell and taste, just kind of very brief overview. And so we can do that at the beginning of class next week because it's 5:19. I'll make up for that 1 minute that I was late coming back from my break. So I'll give you that 1 minute back. You guys have a great weekend. I'm officially finished, but I'll hang if anybody has any